Yeah, thanks. I appreciate, I really appreciate the invitation and the opportunity to present this. I recently put this on archive, in time to this. And um, so yeah, I kind of, what is flow? I hope not to hurt anyone. I will say a few controversial things because I think that there are some aspects of recent developments in heavy ion collisions that prompt us to really think from the beginning and sort of reinvent the bicycle, if you want. And I hope I will argue why, and I hope I will argue the sketch of a solution that I've been developing. So, you all know this. Heavy ion physics is supposed to have found the perfect liquid. This sort of redefined our field, and it also spurred quite a lot of development of sort of hydrodynamics as a theory, of developing hydrodynamics from microscopic physics. Most of you also know why this happened. You have this essentially reasonable estimates of initial conditions and as anisotropies of initial conditions, together with very low viscosity or even zero viscosity. Zero viscosity, I would say, is within error bar, describes quantitatively the momentum anisotropies produced in nucleus-nucleus collisions. Most of you, some of you were in the front seat of developing this, so there is only so much I can say about this. I will, however, say, I'm a theorist, and this is a pretty theoretical talk because this is not quite developed, but the ultimate aim is to understand experimental data. And I would just like to sort of give a couple more sort of reflections on what this experimental data is, because it's not such a trivial matter. So what is the data? The data is this Fourier coefficient, which is called Vn. But this Fourier coefficient is sort of a little bit ambiguous, because if you're a theorist who is interested in sort of more fundamental aspects of hydrodynamics, this is a multiple coefficient that you integrate over volume. But if you're an experimentalist, or someone who does Monte Carlo, then this is some kind of correlation between particles, and it's actually a very non-trivial correlation because it's the expectation value of a cosine, and so it's a cumulant of order infinity. So going from one to the other, there is some wiggle room, and there is several methods on going from one to the other. You can use spectators to define a reaction plane. You can make sure, because the point is that any very basic stuff which has nothing to do with hydrodynamics, such as conservation of momentum, could also give you correlations which give you Fourier coefficients. So obviously you have to eliminate them. And how do you eliminate? Well, you can use spectators to define a reaction plane. So this thing is in terms of a reaction plane. You can use large rapidity separations. Or, sort of more sophisticated, you can do higher and higher and higher cumulants. And you make sure, and this is an experimental data point, that the same Vn appears in multi-particle cumulants. So you have Vn2, Vn4, Vn6, et cetera. Vn2 is a little bit, that's the one that carries most of the conservation of momentum. But so it is a little bit different, but as you go higher and higher, it seems, and this is an experimental result, that this goes to a universal limit, which is truly collective because it involves many particles. So this is, I would say, what I consider to be the most convincing piece of experimental evidence that this is real collectivity. Sure. Yeah. Which brings us to the LHC switched on, and it found something that really should be bugging you. At least it bugs me. And this is why I mentioned this cumulant universality. Because if this is your criterion, then yes, you have a perfect fluid, but you have a perfect fluid everywhere. Essentially, the degree of collectivity, which I would call the matching between orders of different cumulants higher than 2, is completely independent of the size of the system and, more crucially, the multiplicity. This is a pretty old plot. It's from 2016, but more recent plots have increased the order of cumulants, decreased the error bars. At the last quark matter, they went down to 10 degrees of freedom using rapidity separation techniques. And the result, the basic qualitative result is still the same. What we're calling hydro and collectivity does not depend on the number of degrees of freedom at all, or at least it depends on them really weakly within error bar. Four point, 6 point. Okay. Well, with cumulants, you don't really subtract. And I find the fact that things are within error bar, 4 particle, 6 particle, 8 particle cumulants, that's weird. Yeah. Oh yeah, I mean, this is not an experimental talk. I agree that it's a controversial subject. I mean, there are experimentalists with Quiggle, but to me, the evidence simply seems to be that the degree of collectivity seems to be weakly dependent on degrees of freedom. And this is a mystery. So the reason why I find it so troubling, so what is hydrodynamics? What is hydrodynamics? Well, the usual sort of thinking is that you coarse grain, you take averages, you look at observed quantities, and you expand them in gradients. There is some subtleties with relativity. I mean, you have these so-called constituents relations, but the point is that once you do this and you impose some statistical mechanics concepts, you can basically solve the conservation law equations, and they give you all the dynamics. There are issues with causality, so with relativity, you have to extend it a little bit more. So you basically, sometimes, you split this guy into the equilibrium part and the non-equilibrium part according to some matching criteria, and you basically give non-equilibrium part the relaxational dynamics, and then you couple this to conservation laws. And so this is an effective theory. All effective theories are based on separation of scales, and here the separation of scales is what is called the Knudsen number. So it's something like the sound wave dissipation length multiplied by the gradient, or the relaxation time, if you think of relaxation scales, multiplied by the gradient. And the transport coefficients are calculable from asymptotic correlators. So what's the problem with this? We discussed this the day before yesterday. There was a 2-hour, there was an afternoon, very nice discussion session about what a possible problem is. That everything here is sort of expanded, but exactly how you expand is a little bit ambiguous. There are several definitions of the flow. I mean, there is the Landau frame, there is the Eckart frame, there is this BDNK, where the frame becomes sort of an arbitrary vector field. And the nice thing about this is that these relaxation terms become trivial, they become proportional to the gradient. But the price of this is that it's a gradient of something which is sort of not really defined in terms of statistical mechanics, but in terms of certain causality constraints. So this guy is ambiguous, and entropy is ambiguous. And by ambiguous, I simply mean that the dynamics in general depends on the definition of the flow. It's approximately independent, and in fact, in the 80s, there were theorems by Geroch and Lindblom and these other general relativity gods who basically say that as long as you are close enough to equilibrium, the differences don't matter, and if you are far away from equilibrium, you shouldn't be using hydrodynamics at all. However, it's still a little bit, there is no real quantitative recipe to make effective theories which are really independent on how you define flow. And when you talk about close and far away from equilibrium, small systems where you shouldn't have equilibrium at all kind of should make you feel a little bit queasy. I mean, what is the prescription for this? Well, then there is this other elephant in the room, which is, of course, fluctuations, which very roughly are Poissonian. They are 1 over square root of n. They're very small in lead-lead, but they're huge in proton-proton. So the reason why fluctuations are sort of central to my story is, I mean, pretty much all of statistical mechanics is based in some way on fluctuation-dissipation relations. You have fluctuations, they take your system out of equilibrium, but they are small, so the system sort of oscillates around equilibrium. And the basic concept of this is that fluctuation-dissipations are related. The two scales are related. However, at least if you take experimental data seriously, my interpretation of experimental data seriously, yeah, you're basically ruling out fluctuation-dissipation relations because the degree of collectivity is independent on how many degrees of freedom you have. And fluctuations obviously depend on how many degrees of freedom you have. More concretely, I mean, there has been some really sophisticated work, many of whose authors are at this workshop and are sitting here, that essentially say that hydrodynamics isn't really universal if fluctuations become important. I mean, you have non-hydrodynamic modes, you have stochastic transport coefficients, you have long time tails, and essentially they blow up microscopic contributions in such a way that the exact dynamics doesn't just depend on conservation laws, but it depends on the degrees of freedom of the microscopic theory. And in many ways, in many approaches, people arrive to this conclusion, and experimentalists just don't care. They measure angles, they calculate correlators of angles, and they find a degree of collectivity which is independent of degrees of freedom, which actually begs the question on whether all these sophisticated non-hydrodynamic modes are observable, not just in practice, but in principle. In what limit can an experiment or a Gedanken experiment distinguish a non-hydrodynamic mode affecting pi mu nu caused by a fluctuation from, for example, an equilibrium fluctuation? In what, of course, the answer is usually that one is gapped, so it's a short-range correlation, and the other one is a long-range correlation. But what does short and long mean? Well, from sort of, if you try to derive hydrodynamics from sort of field theory, you actually get, and this has been discussed last week, it's actually really complicated and no one really knows. I mean, you have Guy Moore and collaborators who've done a heroic effort to go into loop calculations, and the answer is that the convergence of this to first order, it's basically the Boltzmann equation, but no one really knows how big corrections are, and you have unsurprisingly, because the Kubo formula is an asymptotic correlator, you're going to have infrared divergences that sort of need to be regularized in some way, and it's not really clear if they are mathematical or physical divergences. So usually people do not do this. Usually people do something like this, where you basically regularize QFT using the Boltzmann equation, or you use ADS-CFT, where you can really solve everything, and then you match this to hydrodynamics. You have various Parton cascades that you match to hydrodynamics. And so the question is, do these things have something in common? They actually do, and it's a very important thing. The point is, what happens to fluctuations on a scale of gradients? The Kubo formula is based on the fluctuation dissipation theorem, but the fluctuations it takes are asymptotic. They are, you take the asymptotic, the soft limit, and then you isolate your desired transport coefficient by sort of expanding around small frequencies, which is all well and good, but now you have an effective theory with 3 scales rather than 2. Usually, I mean, the series which has been developed on which most work has concentrated is the second inequality, as I said. So the mean free path, or the sound wave dissipation length, compared to the macroscopic gradient. But then there is this microscale, which is simply the distance between degrees of freedom. And in most UV completions of hydrodynamics, this scale is actually assumed to be 0. I mean, Boltzmann and ADS-CFT are considered to be the opposite ends in the value of the coupling constant, and they are. But in both cases, this guy is essentially assumed to be 0. The Boltzmann equation is valid in the so-called grad limit, where the number of particles per cell goes to infinity, the cross-sectional area goes to 0 in such a way that the number of interactions is constant. I mean, this is the limit. This is what's called the grad limit. This is where molecular chaos is strictly justified. The ADS-CFT is NC squared, and the Young-Mills coupling constant goes to 0 in such a way that lambda becomes large. So the coupling constants do have different limits, but in both cases, the microscopic degrees of freedom is essentially 0. And this is exactly the assumption that experimental data says you should be cautious about, because the microscopic degrees of freedom, we actually know what it is in experiment. You basically take the volume of a proton and you take the multiplicity and you estimate it using multiplicity divided by volume of the proton. That's the initial microscopic scale. And it's at least of the order of the mean free path. Again, if you take my interpretation of experiments seriously. For this reason, I personally, I hope I don't offend anyone, but I find the program of hydrodynamic attractors, non-thermal fixed points, hydrodynamization, and so on and so forth, very unconvincing. Because the people who do this go beyond hydro into the UV theory, but the UV theory is based on the many degrees of freedom. The gradients can be much higher than the hydro expectation value, but you still have degrees of freedom going to infinity. And degrees of freedom are very far from infinite. They are of the order of the mean free path. And in this limit, it's not hydro that breaks down, it's the Boltzmann equation and ADS-CFT that break down, because the problem is not gradients. The problem is that you have very few degrees of freedom in a fluid. So maybe I'm just misinterpreting, taking the experimental correlations and being too literal about applying them to collectivity. Maybe. Yes. Yes. It would be the distance between water molecules. Water, where, yeah, I'm sorry. There is a minus sign missing in the exponent. Thank you. Yeah. Water is actually, yeah, and in water, that's a good point, because the Boltzmann equation is inapplicable to water. You have hydrogen bonds. This is exactly the point. Is there a way to derive hydrodynamics which is independent of this first inequality? I mean, this is where I'm going. Well, in water, you sort of assume hydrodynamics. As far as I know, no one has derived hydrodynamics for water. Yeah, I agree. That's where I'm going. I agree. Mm-hmm. Yeah, but they tend to destroy the universality of hydrodynamics, while the data says that hydrodynamics appears remarkably universal. You know, if you have very few degrees of freedom, the long time tails will dominate, but then you don't have but then collectivity becomes dominated by random fluctuations. Yeah. I don't know. Yeah. I agree. Actually, I agree that you need, yeah. Let me get back to this in a few slides. Yeah. And I just want to say one thing, that if it was just heavy ions, the most obvious thing is maybe we're misinterpreting the data, particularly in small systems. But nowadays, there's been this effort to do cold atoms where you can really put degree of freedom by degree of freedom. They are not quite using the analysis of heavy ion collisions, but there you also have, it seems that you need a remarkably few amount of cold atoms, provided they're strongly coupled enough to get hydrodynamic type behavior. And you actually have, has anyone heard of the Brazilian nut effect? In Brazil, the biggest nut goes on top. It's a, yeah, yeah. If you have a jar of mixed nuts in the kitchen, usually the biggest nut, which is usually what's called the Brazil nut, the castanha de Pará, is on top of the jar. You'll be surprised to know that people write PRLs about this. It's actually still not an understood phenomenon. Huh? It's a what? Yeah. Sure. I know. Yeah. It seems it has something. So the numerical understanding is that if you have a strongly correlated system, which is subject to random fluctuations, entropy is big, even if there are few degrees of freedom, provided they're strongly correlated, the average of them moves as a fluid. Exactly how this works in terms of statistical mechanics is not really known. But I find this, I mean, this is actually, a strongly correlated system subject to random energy fluctuations. This does look a little bit like a hadronic collision. I mean, maybe more than a 5-dimensional black hole with 4 supersymmetries. So this is sort of an intuitive thing. I mean, is there an effective theory of this? Well, I mean, one has to remember that if you think about statistical mechanics too deeply, you go insane. I mean, and in fact, and the question of what does statistical mechanics, what does even equilibrium look like? I mean, hydrodynamics is based on statistical mechanics, but the two don't really mesh together that well. Because a system, if you take a bucket and you show it to a statistical mechanicist, they will say that this is a still bucket, which is described by one partition function. A hydrodynamicist will see if the viscosity is low and the Reynolds number is high, they will see things like wild solutions and the hydrostatic limit being broken by perturbations which actually break the well-posedness of the theory in the non-relativistic limit. So these two things, in particular, whether the Kolmogorov cascade, again in the non-relativistic limit, should be counted as macroscopic versus microscopic entropy. This is something that people are arguing about. And of course, the word entropy, there is actually some ambiguity to the definition of entropy as well. You have the entropy of Boltzmann, which is sort of an objective property of microscopic degrees of freedom, and the entropy of Gibbs, which is ultimately something a result of a Bayesian inferencing of the fact that you cannot distinguish every microscopic degree of freedom. And the two for interacting systems are not the same. They're only the same in certain limits, which are called the Khinchin conditions. I mean, Khinchin was Kolomogorov's graduate student. Kolomogorov told him, look, I formalized probability, now you formalize statistical mechanics. Khinchin wrote a very nice statistical mechanics book, but then he basically went back to his advisor and said, I can't, this is all nonsense. I mean, the statistical mechanics assumptions, and I will get to that in a second, are inapplicable for the great majority of even chaotic systems where they're thought to apply. This particular question might have been solved in quantum mechanics by the Berry conjecture and the eigenstate thermalization hypothesis, which brings us back to this entropy being high. It seems that quantum systems whose classical counterparts are chaotic and whose energy levels are high, above 1, not necessarily the number of degrees of freedom is high, but the energy per degree of freedom compared to the ground state is high, seem to be bored in equilibrium in the sense that their density matrices seem to be very close to pseudo-random matrices, and essentially from there you go to the microcanonical limit and you can derive the rest of statistical mechanics. So it seems that if you have quantum mechanics of strongly correlated systems, which are non-integrable, and you put in enough energy, they do thermalize remarkably fast. But fluctuations, unlike water, for example, in water, fluctuations in a macroscopic body of water are small. Here, fluctuations are overwhelming, and what we need is an effective theory which sort of respects causality, where in every cell things are born in equilibrium, but the number of degrees of freedom in every cell is really of the order of 1. And sort of random fluctuations talk to each other, and we need an effective theory of that sort of thing. And as far as I know, we don't really have one, or at least I've been trying to work on developing this. So, on developing this, and this is exactly the effective theory which would go beyond the grad limit and beyond large and C. So how can you do this? Well, there is a totally different way of looking at Lagrange, the hydrodynamics that I've introduced so far is Eulerian hydrodynamics, which basically means that you're sitting in a lab and you're watching conserved currents flow by. But there is a usually completely equivalent definition of hydrodynamics, which is Lagrangian hydrodynamics, where instead you're sitting in a cell and you're watching the cell flow and you're also watching the cell sort of spin around and deform. Most numerical codes are based on Eulerian hydrodynamics for a bunch of reasons that I will explain a little bit more, but Lagrangian hydrodynamics is sort of really elegant. I mean, the point here is that your degrees of freedom are the 3 coordinates of your cell, and the dynamics can be uniquely determined by the symmetries, by the reparametrization symmetries. I mean, the 3 coordinates are coordinates you set, and then it turns out that you have a very big group of symmetries, which is invariance under volume-preserving diffeomorphisms, which will uniquely specify the dynamics of an ideal fluid, which is uniquely defined. In this case, you will have a unique vector that is going to be fixed by by taking the gradient of these coordinates and taking this vector proportional to this gradient. And it turns out that this is a generally covariant equation under these volume-preserving diffeomorphisms. You can also put in a finite chemical potential. Son, Dubovsky, and collaborators wrote this really nice paper about this, where you basically promote cells to complex phases because internal conserved charges are Noether currents of these phases. And then you extend the diffeomorphism to the phases. So the phase can be a random, it can be an arbitrary function of these coordinates. So the phase can be an arbitrary function of these coordinates. And it turns out that these two guys are exactly equivalent to ideal Euler equations. I mean, that's nice because this looks like general relativity, and general relativity is beautiful. I mean, we know that hydrodynamics is in a sense similar to general relativity. It's not the same because these are volume-preserving diffeomorphisms in a three-dimensional Euclidean space, and also dynamics is not sensitive to curvature. So this is different. But the similarities are more important than the differences, in my opinion, because it's a generally covariant theory under a certain group of diffeomorphisms. So the question I was asking previously can be reformulated into about what's the role of fluctuations, can be reformulated by, do fluctuations break these very profound symmetries? I mean, you know, this is, hydrodynamics is GR for poor people, this is quantum gravity for poor people. How do is it possible for fluctuations, microscopic fluctuations, not to break these symmetries? Well, before asking this, one has to ask, okay, I mean, these volume-preserving diffeomorphisms are really nice and cool, but what does this have to do with statistical mechanics? The whole coarse graining procedure, in Eulerian hydrodynamics is obviously related to statistical mechanics. You have lots of molecules, so you take averages, they thermalize, so you use conserved currents because they're the slowest degrees of freedom. What does this stuff, what do volume-preserving diffeomorphisms have to do with statistical mechanics at all? Well, it's the largest group of diffeomorphism that you can invent where time plays absolutely no role, these volume-preserving diffeomorphisms. So what does this mean? What could this mean? Well, in statistical mechanics in equilibrium, time also plays no role. The reason time plays no role is because ultimately statistical mechanics comes from the ergodic hypothesis. The idea that in some limit, the evolution becomes independent of time because time averages are equal to some probability distribution, which is itself independent of time. And then in the context of physics, this is sort of mathematics, this is not physics, but in the context of physics, this guy will be a bunch of delta functions which are which correspond to conservation laws. So what's wrong with this? Well, what's wrong with this is that this is not covariant, obviously, because this guy here is some kind of microscopic thing, and this guy here is time, and here there is a whole bunch of stuff which doesn't depend on time at all. So this is not relativistically covariant. So what can you do? Well, one thing that you can do is foliations from, remember, the ADM formulation of general relativity has that. So instead of time and space, you have the time-like component of the 4-vector, the space-time component of the 4-vector, and you can basically promote time as a function of the space coordinates. These are generally non-inertial frames. And you will have diffeomorphisms in terms of non-inertial frames in between them. So is this covariant? No, of course it's not covariant. I mean, you've just written it with a bunch of Greek letters so that it looks covariant, but it's not covariant because over here you have something that depends on time, and over here you have something that depends on sort of 3 volumes. So what can you do? You can try to ask yourself if there is an effective theory where the ergodic hypothesis is valid for every single foliation. You can ask yourself if there is an effective theory where the ergodic hypothesis is valid independent of foliation. And now you're kind of getting somewhere because you remember that these guys are delta functions within physics, which, I mean, we're talking about ergodicity from microcanonical statistical mechanics. So these are delta functions with conservation laws, and conservation laws are coordinate transformations. They are space transformations for the momentum current, and they're phase transformations for internal symmetries. And then you also remember that these foliations, I mean, this is the Cooper-Frye formula, they decompose. I mean, this is a 4-vector, but it's dependent on these 3 parameters. And you can decompose them into a Lorentz transformation times a sort of volume stretching. So you can stretch this coordinate, you can stretch this coordinate, you can stretch this coordinate, etc. So if you take conserved currents and you do a reverse of the Noether theorem, and you remember that delta functions are, and you remember that delta functions, the delta function of a multidimensional function is going to be 1 over the Jacobian, you get exactly the volume, you get exactly the symmetries of fluid dynamics. You get exactly the symmetries of fluid dynamics. Essentially, the effect, if you want an effective theory which looks ergodic in an invariant way under foliations, your degrees of freedom are going to be the 3 spatial coordinates with which you, parameterize the foliation thing, and the phase for internal symmetries. And then the symmetry that you have to impose is the volume-dependent diffeomorphism. So this is really nice. This is something that has been bugging me for many years. I started working, I learned about this Lagrangian hydrodynamics as a field theorist from a cosmologist in Columbia University. It bugged me for many years. What does this have to do with statistical mechanics? I credit Dam Tam Son entirely for giving the right intuition on this for me. I mean, it's discussions with him that sort of got me thinking on this stuff. And it's really nice because this is sort of ergodicity doesn't actually mean small fluctuations. If you want ergodicity Gibbsian hydrodynamics to be equivalent to Boltzmannian hydrodynamics, yes, it does. These are the so-called Khinchin conditions. But in general, you can define ergodic systems which are highly fluctuating. So this is sort of nice because you can, it's at least a way of seeing how hydrodynamics could emerge and the symmetries of hydrodynamics could emerge in a highly fluctuating environment, which is chaotic enough that the ergodic hypothesis is valid. However, there is a problem because we're only thinking about ideal hydrodynamics. And in fact, one of the reasons why Lagrangian hydrodynamics is less popular among numerical simulations is because in Lagrangian hydrodynamics, putting in non-ideal terms is much more tricky and somewhat model dependent. It has been done, but there is no sort of obvious way to do this. Yeah. So anyway, how do you extend this sort of symmetry and diffeomorphism picture to non-ideal hydrodynamics? Well, the way that I'm trying to do this, and now we come to the paper that was put online about a month ago, is the following recipe. I mean, what we're trying to do is we're trying to formulate the theory in terms of generating functionals. So fluctuations and these generating functionals aren't simply things that you take averages of in coarse grain. No, you maintain these probabilistic objects that generate cumulants in every cell, and you try to write an equation on how these objects transform. So your theory is quintessentially defined. Fluctuations are not something on top of a background. Your theory is an ensemble that evolves. So you have an ensemble as an initial condition, and then you bring this ensemble forward using some equation of motion which applies to generating functionals. And the fundamental principle about which this theory should work is the fact that you can refoliate and you're moving around the ensemble, but it's the same ensemble and the same equation of motion. And this is, again, sort of a general covariance type issue, because if you take your arbitrary foliation and you differentiate by the same foliation, you get a metric. So things should be covariant. So this generating functional and its dynamics should be covariant with respect to the metric. And this has to do with statistical mechanics, because this principle, I mean, physically what this means is that close to local equilibrium, you should, if you see a small step in the generating function, if you see a small step in the evolution of one point of the ensemble, you should not be able to see, you should not be able to determine locally whether this is due to a fluctuation in equilibrium, or whether this is due to a generally dissipative evolution. Over many steps, of course, you see this, but locally, it should, in principle, from the definition of the generating functional, be impossible to see this. And finally, what are changes in this guy? Changes in this guy are exactly changes in what you call flow, are exactly changes in what you call pi mu nu. So essentially, this theory, the dynamics should be manifestly just be a function of T mu nu of conserved currents and of their fluctuations. I mean, it shouldn't just be a function of T mu nu, it should be a function of T mu nu and the fluctuation of T mu nu. Rather than decompositions like the Landau frame, the Eckert frame, et cetera, et cetera. I think dynamics should strictly be independent of the choice of flow, and you implement this by making sure that the dynamics is covariant with respect to refoliations. So this is a different way of looking at hydrodynamics when you build up your theory as a sort of non-perturbative fluctuating theory, and you impose the symmetries of Lagrangian hydrodynamics. In principle, this could really make a difference in hydrodynamics in small systems. And the reason for this is that what happens to fluctuations, which are, I mean, there is actually a physical analogy, which is renormalization of gauge theories, the role of gauge symmetry in renormalization. Why is this? Because sort of functional integrals in gauge theory, you define them as integrals over all configurations of potential, but you have shifts in the variable which are proportional to gauge, which are equal to gauge shifts. So many fluctuations, in particular, many high momentum fluctuations, are reconducible to gauge shifts. And these things do not change the action. And if you look at it carefully, this is sort of the reason why the theories, why gauge theories tend to be renormalizable, because a great majority of fluctuations are things that do not change the action, and therefore they just become a normalization thing. In hydrodynamics, this picture about microscopic fluctuations and the difference, the fact that locally you have this invariance between fluctuations and dissipative dynamics, sort of have the same role. Because what we are saying is that a fluctuation that is equivalent to a change in foliation. So for example, a fluctuation that is equivalent to taking your Landau frame theory and making it into an Eckert frame theory or a BDNK theory. This is not a physical fluctuation. This doesn't even change the microstate. This is simply a different way to look at the theory. And as you decrease the number of degrees of freedom, yes, you increase fluctuations, but you also increase this number of non-physical fluctuations in some way. So this is very similar to sort of a gauge theory. And this comes from the fact that sort of the Zubarev statistical operator is proportional to this T mu nu beta mu d sigma, and you should be able to reshuffle d sigma, change beta mu in such a way that this free energy type object is invariant. And in this case, the great majority of field configurations which leave this guy invariant are not physical fluctuations at all. So, is there a way to do this? I mean, so far, this wasn't the theory. So far, this was a wish list. So how could you do this? Well, let's make an additional simplifying assumption that I'm basically pulling out of thin air. the partition function is approximately Gaussian. Why? Because every probability distribution is approximately Gaussian, unless you're like close to a critical point or something like that. And because I can solve Gaussians. And because I can even do functional integrals with Gaussians. So your partition function is approximately Gaussian. What does this mean? It means that it's characterized by two fields. This is not a Gaussian, this is a functional Gaussian. So it's a Gaussian at every point. Think of a lattice, and there is a Gaussian at every point. And a Gaussian is characterized by two things. You have an average, and you have a fluctuation. And very roughly, this is sort of similar to quantum field theory. The fluctuation is the Green's function. The average is the field configuration at that point. So you have an average, and so your Gaussian is characterized by two parameters. And here comes an interesting thing. For Gaussians, and only for Gaussians, the gravitational word identity, which is the equation that reinforces general covariance, I will explain this in detail in a couple of slides, is exactly what entirely determines the dynamics. So in principle, if you assume the partition function is a Gaussian, you will get a differential equation that relates the fluctuation to the average, which determines the whole dynamics. So the dynamics is just these two assumptions. The only problem is that you also need fluctuation dissipation, you need something like linear response, and you need to make sure that linear response is also generally covariant, otherwise these 2 points are inconsistent. So what is the gravitational word identity? It was derived by Deser and Boulware in 1967. You have the propagator between two energy momentum tensors, and it's related to the average by this relation here. It's called the gravitational word identity, but it actually doesn't really have anything to do with gravity. It simply says that local fluctuations of T mu nu should be understood, can be parameterized as local coordinate transformations. Because if they aren't, T mu nu ceases to be the Noether current of local spacetime diffeomorphisms. I mean, that's all it is. It is used in Kubo formulas. Uli Heinz and Sang-Yong Jeon, in their review of hydrodynamics, they have a very nice discussion where this is done in gory detail. And here you actually see the difference between what are Lagrangian symmetries and the gradient expansion. Because what do? They write down this formula, they choose a hydrostatic background, and then because of this delta function, this guy here is the only term which is there, and then they derive the Kubo formulas from this. These so-called contact terms are neglected. But they're neglected because this is not a generally covariant theory. You've chosen a frame. I'm trying to keep general covariance, so I need this whole expression. And in fact, you already see that for this whole expression to be valid exactly, this guy, this correlator, cannot just be a function of the Lagrangian. It's something that you solve for. It's something that is there in the initial conditions, and you solve T mu nu, and you solve this guy here, and you kind of solve them by going backwards and forwards in the equations of motion. So then you assume that the partition function is Gaussian. What does this mean? It basically means that at every point, you're going to have this T mu nu minus T mu nu average, T alpha beta average, and they get contracted by some rank 4 tensor, which is the width. It's the covariantization of the energy fluctuations. And then, of course, we all know how to solve Gaussians. It's a little bit more difficult because this is a rank 4 object and these are two rank 2 objects, but it's actually possible to do with a few tricks. And indeed, it turns out that your Gaussian is going to be a very similar form to every Gaussian integral you come to love and love, but the kernel is so this is generally covariant, and the reason you can write a generally covariant theory like this is because you have two frames here. Because in general, the average and the kernel are not really at rest in the same frame. So essentially, this guy here is going to be a function of the kernel in the rest frame of the average times the eigenfunctions, eigenvalues of the average, which we know as pressure, as generalizations of pressure and energy density. The gravitational word identity becomes an old-fashioned, complicated conservation law equation. It becomes something like this, where you have the kernel evolves, but the kernel evolves in a way that is sensitive to the frame where the average is, and so this is the evolution equation. It's complicated, it can be solved. The language I've written this looks very different from the language of the usual hydrodynamics. But in fact, if you look carefully, you have really familiar objects here, because this kernel is the generalization of the energy fluctuations, which are functions of the heat capacity. And instead, you're going to have this object here that, well, beta mu d sigma. And also transport coefficients, if you look at Kubo's formulas, transport coefficients are going to be related to the asymptotic behavior of the kernel. They're going to be related to asymptotic behavior of the kernel. But it's only the asymptotic behavior, which of course becomes a good approximation when the gradient expansion is a good approximation. So when the gradient expansion is a good approximation, then what happens in the middle sort of becomes irrelevant, and only the asymptotic values determine the kernel. But in general, this kernel is an object that evolves in time, that you get its initial condition from fitting a Gaussian to the initial value of the ensemble, and then you use this equation here to evolve it forward in a way that the gravitational word identity is exactly satisfied. So finally, does this make sense? So this is consistent. The Gaussian assumption is arbitrary. So for this to be true, it has to at least make some kind of logical sense. So does this make sense? And an obvious objection is probably not, because you need linear response theory to be generally covariant. And linear response theory is another thing that looks really non-covariant, because you have an object. What is linear response? You have a perturbation, and then you have some kind of kernel that includes fluctuation dissipation relations. You impose causality relations, and you're going to get the response at some moment in time. And you impose causality relations using these standard procedures where you do this in the complex, extend to the complex plane and make poles, et cetera, et cetera. And this is not generally covariant because this guy depends on sigma zero. This is not generally covariant because this guy depends on sigma zero. Also, another thing that should make people really skeptical, I mean, certainly it made skeptical a lot of these linear response experts with whom I talk to, is that you have fluctuation dissipation, but the exact relation between fluctuation dissipation is a very complicated thing that you get from something like the Kramers-Koenig relations. You go to the complex plane and then you enforce things. So here you need general covariance. Here you need general covariance to essentially relate the real part and the imaginary part. And this is consistent. And this is consistent with what I was saying earlier. This has to be true if the theory has the property I was talking about earlier about the local equivalence between fluctuation and evolution, fluctuation and dissipative evolution. That the relation really has to be dictated by general covariance. So, but what kind of theory would have this property? What kind of theory would have this property of a general covariance of this correlated here? It turns out that it's exactly the theory which is invariant under volume-preserving diffeomorphisms. So these volume-preserving diffeomorphisms, the standard view in the literature, and by the standard view, it includes me in one of the first papers I wrote on this subject, but of course there is, other people, other more famous people who've done much more thorough jobs than me. The standard view is that volume-dependent, the volume conserving diffeomorphism invariance is a property of ideal hydro only. Dissipative corrections break this. However, it turns out that if you impose volume-preserving diffeomorphisms, you also get a generally covariant linear response equations. And if you think about it for a second, this is exactly why the whole thing is consistent. Because the theory, I mean, my physics assumption was this local indistinguishability between a local fluctuation and dissipation. So they're only distinguishable globally, but they're not distinguishable locally. And if this is true, you kind of expect the symmetries of ideal hydrodynamics to be present in non-ideal hydrodynamics, provided that you have both fluctuations and dissipation. I mean, this is what you're physically doing. These volume-dependent diffeomorphisms are still there. They're hidden in this general covariant stuff. But they're not only present at the average. You need the kernel and the average to really see them. Yes? Yeah. Okay. I will. I think this answer, this guy here, this slide is exactly what is exactly the direction in which you need to go to answer this question. If you you can write this using linear response theory, but this is actually related to imposing the Crookes fluctuation theorem in every piece of the dynamics. So what is the Crookes fluctuation theorem? The Crookes fluctuation theorem, equivalently, there is something called the Jarzynski inequality, which is a bit more used in high energy physics. So the Crookes fluctuation theorem is something that is derived from mesoscopic hydrodynamics. It basically says that the probability of work being done of the probability of the heat bath, the probability of the system of a system in equilibrium you have a system interacting with a heat bath, and usually the system does work by transferring heat to the heat bath. But what breaks the second law of thermodynamics is the heat bath transferring heat to the system receiving work from a heat bath. The Crookes fluctuation theorem essentially says that this can occasionally be broken, but the probability of the system doing work by transferring heat to the heat bath with respect to the reverse process is the exponent of the difference in entropy by the work being done, the increase of entropy by the work being done. If you think about the Boltzmannian definition of entropy, this is obvious. You're changing the number of microstates, and every microstate is equally likely. However, Crookes derived this. I mean, Crookes is alive and is not even that old. Jarzynski is alive and is not even that old. This was derived, I think, in the early 90s. And the point is that this was derived in situations where Boltzmannian hydrodynamics is inapplicable, like quantum systems being in equilibrium with heat baths. In the Markovian limit, you also need Markovianity. You cannot have a memory effect. Here we don't derive, mathematicians prove things rigorously, physicists prove things vigorously. I'm being extremely vigorous here. The Crookes fluctuation, this is the Crookes fluctuation principle. But it answers your question that microscopically, it answers your question. So microscopically, microstates are equally likely. So there is certain probabilities. I mean, you have non-perturbative fluctuations, so entropy is as likely to jump down as to jump up. Entropy is as likely to jump down as to jump up. However, because there is more microstates, on average, of course, the entropy jumps up. But at every microscopic step, if you consider things in equilibrium, if you consider things in equilibrium, you have the equality of microstates. So I think, I mean, this is a really subtle issue that I'm still thinking about. But I think the answer to your question is that you have to consider, you cannot consider what C and average are. They are quantities that you get from an ensemble. And if you look at every microscopic possibility of what the ensemble can do, you are going to get not entropy current invariance, but you're going to get every microstate being equally likely. And this will be true independent of foliations. And this will be true independent of foliations. And that's why when you look at both the variance and the mean, this is why when you look at both invariance and the mean, you will have the emergence of volume preserving diffeomorphisms. But if you only look at the mean entropy is going to increase, and of course you break it. So you need the fluctuation and the mean, and you need to consider entropy as a Gibbsian sort of Bayesian entropy. You don't know what entropy is. You sort of reconstruct it from the microscopic equality of microstates. I mean, this is the best answer to your question that I can give at the moment. Yeah, but in any case, one thing I can tell you is that you can get Crookes fluctuation theorem from linear response theory. So you can rewrite all of this in terms of Crookes fluctuation theorem, where you get entropy from these logarithms of z at every point in time. And the Crookes fluctuation theorem applies in every single foliation. So it does seem to be consistent. The Crookes fluctuation theorem, by the way, you can reproduce several sanity limits. I mean, if you take a contour of the Crookes, if you apply the Crookes fluctuation theorem to a contour which is isomorphic in space, you get the Boltzmann entropy principle. And if you take the Crookes fluctuation theorem and you apply it to a contour which is a little bit at epsilon in space and time, you also get the Kubo relation. So you have some sanity checks in this, which is nice because, as I said, it's not a theorem. It's not a theorem at the moment. We simply assume it to work. And in the limit of infinitely many degrees of freedom, this guy here becomes a delta function, and it becomes a delta function of the entropy current. It becomes a delta function of a conserved entropy current. So here is what happens. Here's why we get a smooth limit, and this is sort of answers your question as well. There is no consistent limit in which dissipation is non-zero and fluctuations are zero. There is no consistent limit where you have to take both the ideal limit is the limit when both fluctuations and dissipative terms, they go to zero. And they go to zero together in a way that respects general covariance. So volume preserving diffeomorphism. So what is that volume exactly? Well, the volume is sort of the volume of a cell. And the ideal limit is when the cell goes to zero with volume preserving diffeomorphisms being respected. And of course, if you take any function with a certain amount, any peaked function with a certain amount of symmetries, and you take this as a delta function, this delta function will hide these symmetries. But if you consider both the fluctuation, if you consider at the distribution level, these symmetries should be maintained and they're related to general covariance. That said, it is actually a theory in principle you can solve, probably with a computer. All that you have to do is to take your kernel, use this kernel to integrate the average of T mu nu, and then take the word identity and use the word identity to reconstruct the kernel from the average, and then you repeat at every point in time. It's a complicated calculation that can probably be done numerically because you need a lattice of points and you need an ensemble, a lattice ensemble at every point in space. And then you sort of reconstruct the kernel and the average from the ensemble at every point in time. So this is not a simple calculation. I it will be nice to see it in a one-dimensional system. This is obviously on a to-do list. But in principle, for a Gaussian, as long as your generating functional is Gaussian, all of the dynamics is reconstructible from linear response theory or from Crookes fluctuation theorem and from the word identity, which sort of gives you all the dynamics. So, I'm kind of running out of time, right? Just to sort of try to, I mean, this has been sort of really abstract. What does this have to do with the question I posed in the beginning about fluctuations and such? Well, there are two scales. You have the micro fluctuation and you have the mean free path. And the conventional hydrodynamics is all defined here. So it's defined where the micro fluctuations are sort of set to 0. Here you have some kind of mass of 1 billion correlated particles which also fluctuate, possibly in a quantum way. What I'm trying to do is sort of the limit where this guy here is actually sort of even larger than the mean free path. And the thing is, because this general covariance makes most fluctuations non-physical, we actually do not know how fast is the approach of ideal hydro from a hydrodynamics like that. We actually do not know how close to ideal hydro every point here is. And in fact, so what is the equivalent of the Knudsen number for a theory like this? Well, I mean, what you're doing is you have an ensemble whose typical point is some distance away from equilibrium. And what you are looking at is you are comparing how distant is the ensemble to the fluctuation. You're comparing the distance of the ensemble from equilibrium with a typical fluctuation size. You're comparing the distance from the ensemble to a typical fluctuation size. Because if it turns out that the system is within one fluctuation size away from equilibrium, then the applicability of Crookes fluctuation theorem essentially says that its evolution is going to be an oscillation up and down from local equilibrium. And this is not the Knudsen number. The Knudsen number is something very different. And of course, it's only based on averages. You take the difference with equilibrium and you compare it to sort of the equilibrium entropy value, and you have a unique definition of flow. Perhaps you want the definition of flow that minimizes the Knudsen number. Here, it's something like this. And in particular, for smaller systems, this guy here increases. So, sort of the standard view based on fluctuation dissipation theorem without general covariance says that the Euler limit is a limit where you take the number of particles to infinity. Certainly if the number of particles is small, certainly the number of particles, if the number of particles is small, you cannot have local equilibration. But if you also impose this general covariance issue, it might actually be that achieving something close to perfect fluidity from here might be much easier than achieving something like perfect fluidity from here. I mean, here we know, I mean, this series is very well developed. We kind of know how Boltzmann converges to Israel-Stewart and Navier-Stokes. We kind of know how holography converges to Israel-Stewart and Navier-Stokes, and we sort of know how big are the successive gradients and the successive corrections to Euler equation. It could be that this series has a much smaller convergence than a stochastic series defined by this. At least it's a reasonable idea. And that would justify hydrodynamics in small systems. As a sort of, this is sort of the end, I would like to, I would like to say that I think if one extends this to spin hydrodynamics, one will also get a dynamics which is pseudo-gauge invariant. And the reason for this is the fact that mathematically a pseudo-gauge is sort of a relatively trivial thing. It's a rank 3 antisymmetric tensor and you take a gradient of it. But physically, there is a very nice review of this by Thomas Brauner. Physically, you can think of pseudo-gauges as simultaneous field redefinitions and coordinate transformations that leave the action invariant. So if you have general covariance and the dynamics where fluctuations and yields talk to each other, in a similar way as Dyson-Schwinger equations, you should be able to enforce coordinate transformations. In the non-relativistic limit, there are actually concepts, recent developments in non-relativistic incompressible hydrodynamics are sort of touching on concepts which are a little bit similar to what I'm talking about here. There is something called spontaneous stochasticity. This is the main point. And the main point is that you can't take the Reynolds number to infinity unless you also take fluctuations to zero in a correlated manner. So this is known as spontaneous stochasticity, sort of. If you take incompressible turbulence as a renormalization group problem, fluctuations, and you cannot simply take fluctuations to zero while the Reynolds number goes to infinity. You have to take them in a correlated manner. So this makes me think that one of the things I'm trying to do right now is to sort of take the non-relativistic limit of what I'm doing, which is a little bit ambiguous, and try to relate this to spontaneous stochasticity, which is nice. One of the top experts on this is in Brazil. And so this is sort of a nice place to stop. I mean, I think that fluctuations in fluid dynamics are not well understood. And I think that if you impose fluctuations on top of a non-relativistic theory, you will always have problems describing, I mean, experimental data, in particular hydrodynamics in small systems, kind of poses a challenge to the naive inclusion of fluctuations using sort of perturbations on top of a deterministic theory. One needs a non-perturbative theory of fluctuations. And the freedom of refoliation, I mean, general covariance, which in this case simply means that physics dynamics is independent of how you refoliate, could actually explain this. It could actually give you a version of hydrodynamics where paradoxically, because of the fact that dynamics is independent of refoliations and because of the fact that as fluctuations grow, so possible refoliations within the ensemble grows, this might actually paradoxically yield the idea that strongly coupled, I mean, you need strong coupling because you need equilibrium for every refoliation. I mean, this was the ergodic idea I had. I mean, you need a strongly correlated system because no matter what you define as time, you should have the system dominated by phase space. So you need refoliation. But once you have this, you might be able to have large fluctuations and few degrees of freedom, but on average, the system really looks like the Euler equation. And hopefully, this might be an explanation for hydrodynamics in small systems. Thank you very much. Sorry for running over time. Yeah. Schwinger-Keldysh is not independent under refoliations. When you are taking Schwinger-Keldyshes, you have a thermal background, and then you use the analytical properties to shift I beta, to shift time so that it has this I beta component. It's also an asymptotic expansion. With Schwinger-Keldysh, you get the limit of fluctuations for large distances, like in Kubo formulas. I mean, look, I mean, in Schwinger, what is the approximation behind Schwinger-Keldysh? The approximation behind Schwinger-Keldysh is you divide things between slow and fast degrees of freedom. Yeah, sure. But it's an effective field theory that, I mean, what I'm looking for is you have a theory which is so strongly coupled that you can define time in every causal way. I mean, remember, you have relativity of simultaneity. And for every, you could invent sort of a local refoliation. You have relativity of simultaneity. Things which are simultaneous in one reference frame are not simultaneous in the other. Refoliations are global things. So you can even, for space-like separations, you have this Andromeda paradox. You can make past and future switch as long as you are in space-like, as long as you keep in space-like differences. So you need a theory where the local dynamics is so strongly coupled that no matter how you refoliate globally, at every local point, every microstate is equally likely. So the system is approximately ergodic. So locally at every point, you do not know. I mean, what does this have to do with ideal hydrodynamics? Locally at every point, you do not know whether you have a ideal dynamics with a fluctuation. So your system is in equilibrium, but it's not at the equilibrium doesn't say it doesn't say that the system with the macrostate with the biggest number of microstates is certain. Equilibrium says all microstates are equally likely. So you do not know whether your dynamics is out of equilibrium locally because you are far away from the average or because the system is really evolving in non-equilibrium. This is the symmetry that I'm imposing. This is where general covariance comes from. So in a sense, locally, the system looks like ideal hydrodynamics. This is fluctuation dissipation. You cannot distinguish local fluctuations from dissipation. I've just added refoliation and dependence on top of that.
Let me just come back to the separational scales that you showed last slide. So you said that hydro needs this separational scale, but let me say that.
Oh, wait. Yeah. Where is water here? Yeah, water is somewhere here. Yeah, no, I think water is close to the Euler equation, but it's in this complicated, because what happens in water is that water molecules have the hydrogen bond, so they're very highly correlated. Yeah.
Density of molecules is the same as mean-free path. Most liquids. So this is what my question is whether. So I don't see why you need to have a first inequality.
But in water, the first inequality is satisfied. Yeah. Yeah. You don't have particles, but you have wave functions of particles. I mean, it might be possible. You're talking about strongly correlated quantum systems. But I just want to say, in water, this inequality holds. You're simply away from this regime and this regime. No, all of them hold. Because for water, the sound wave dissipation length is order of millimeters.
Same of the distance, the average distance of molecules. At least if you take the definition of n minus 1/3.
The sound wave dissipation. I mean, no, the mean free path, careful, because the mean free path is something that is well defined for like gases, for ballistic systems. In water, the equivalent of the mean free path is the sound wave dissipation length. And that's much bigger than intermolecular. I mean, here, E over ST, that doesn't need a mean free path. Yeah. So this guy here is of the order of like millimeters, as far as I know. Yeah. This guy here for water is of the order of millimeters. Yeah. No, not molecular distance. You take a small sound wave and you watch it decrease. I mean, that's what it is. All right. All right. Yeah.
Thank you.